Now in this experiment of FET, the first characteristic that we measure is the output characteristics, that is the source drain current as a function of source drain voltage. Now the current is normally of the order of few milliamperes and the voltage is varied from around 0 volt to 30 volts. In the beginning, we keep the gate voltage 0, that is, we connect the gate to the source and we measure the output current. You will see that initially up to a very small value of voltage, about 2 to 3 volts, this output current linearly increases and then gets saturated and remains constant, wherein if you increase the source drain voltage beyond a certain limit, suddenly the current shoots up and this indicates a breakdown region. So breakdown means the semiconducting channel which you are using as a FET channel has got a certain breakdown strength, and if you surpass that, there is a avalanche current which will flow through the channel. Suppose now we apply a negative bias to the gate and we call this bias as either VGG or VGS. So the voltage is applied to the gate, negative voltage with respect to the source, and we keep a fixed value of this VGS like -1 volt and again repeat the output current measurement. This time we will notice that the saturation current is less compared to what we had observed earlier for VGS 0. And consequently, if we go on increasing the negative gate bias and record the source drain current, you will see that this current will keep on reducing. Saturation current will have a lower and lower value. So initially let us see why there is a linear region and then there is a saturation region. Now initially when you are increasing the value of the voltage between source and drain and the gate voltage was 0, always there is a negative biasing because the drain is positive and gate is negative, and that actually shows you the negatively biased diode junction. So even if it is 0, it is a negatively biased junction, wherein if we make the gate region more and more negative, this negative biasing will keep on increasing. So this channel becomes narrower as the depletion region increases. Now actually this rectangular box that we are indicating here for FET is a cross-sectional diagram, and in practice there is a 3-dimensional symmetry. But for practical purpose, for understanding the mechanism, it is sufficient to assume that there are two similar identical gate regions on either side, left and right side, and the channel keeps getting quenched or becoming narrow and narrow when we increase the gate bias. So that is what usually you draw, that is left and right side there are two P regions and down below is source and upper terminal is drain. Now these measured current characteristics when you plot will look like parallel lines, horizontal and parallel to the x-axis, and this is known as the output characteristic, wherein from here you can derive or either you can measure the another characteristic, that is as you change the gate voltage, how output current will be varying. So you will be changing the gate voltage from 0 to say -4 or -5 volts and measure the output current, source drain current, which will consequently become equal to 0. So, this is known as a transfer characteristic.